standard form of the quadratic equation. And that word is so confusing. So to kind of clarify that too a little bit, because remember when we learned how to solve quadratic equations and we said, put it in standard form. And that definitely, it's kind of like there's two standard forms, and there is the standard form of the quadratic equation, that's when everything's all together, or there's the vertex standard form. Actually, that should be down here. Standard form, I would call this the vertex standard form, because if it's in this form, then you can pull the vertex out of it very quickly, right? We love it when it's like that. At least I do. It's a little less math. Not that you're not capable of finding it, just has a couple steps that you have to find the vertex if it's in standard quadratic equation form. So both the word standard is used, so hopefully that clears that up just a little bit. But we want to be able to take maybe an equation that's in quadratic equation form and convert it into standard form. And one way is to use the completing the square method. But I just think it's easier if you just go find your vertex and put it in standard form. It's kind of a shortcut. And I don't know about you guys, but sometimes I look for those shortcuts maybe too frequently. But that's how I'm going to show you today, because we don't do it that often. We don't really have to put it in standard form that frequently. So if you were given this equation like this, you would have to go find the vertex. And remember, to find it, we'd say negative b over 2a. And so we take negative 4 over 2 times 1, which gave us a negative 2. I already kind of showed you the vertex, but I thought I better go ahead and just take you through those steps. So then we would take negative 2, square it. We take 4 times negative 2 plus 1, and when you plug that into your calculator, you get a negative 3. So we find out the vertex, and you have to know that anyways for that question in WebAssign. And so it's just so quick and easy. If when they tell you to put it in standard form, they'll have a y equals in a box, is to just go the exact opposite of what you learned on how to pull it out of the equation. So you always have an x binomial squared, and we use the opposite sign when we pulled it out, so it'd have to be a positive 2. And then we use the same sign of our y value of a negative 3. Okay, and so let's say you went through all the process to find the vertex of that next example. So just for time, I'm not going to go through those steps again since we just reviewed it. But the vertex of this parabola would be 2, 8. Okay, the difference between this is if you ever have, like when you put it in standard form, a really quick shortcut is if you ever have anything in front of x squared, even if it's a number, but you're not really going to see that in WebAssign, but you might see a negative, you're going to pull a negative out. And then everything else that happens in here is the exact same. Okay, so you're going to say x minus 2 plus 8. And then and this is squared. And then if you were to go through and FOIL this, distribute, and go through that, you would get the same exact solution for your, it would go back to that, I guess is what I'm saying. So that's just a shortcut, and that's how you'll turn it into standard form. Mostly you're doing that in WebAssign. You know, WebAssign only has so many questions in their question bank, and I can't control them. So that's why I've needed to kind of alter my notes a little bit, because it's like some concepts that I'm not really teaching, but we could do because it's just the inverse operation of what you've already done. Okay. And then something else I'm going to talk to you about before we move on to 2.5 is the terminology that changes, and you're going to see a question that says find the real zeros of a quadratic. Okay, so these would be the instructions. It would say like find the real zeros of this. Well, this is just solving a quadratic equation for x. It's just a new terminology, which we can also say x-intercepts. So I like to introduce that to you because it is pulling from a previous section. And I just wanted to go over that with you. So like if you look right here at this quadratic equation, if they tell you to find the real zeros, what are we trying to do? We're trying to zero out that quadratic, right? So that's when you would replace the y with a 0, like we've talked about before. And then we would go factor and solve that quadratic equation. So what do we need to do first when we factor this? Can we have a negative in front of our leading term? No, so we pull out a negative, and that changes all of these to just the opposite. So this should be hopefully a review for you. I know we had a day off, so sometimes we gotta brush off the cobwebs of math. Remember using opposite signs to factor this, since that last term is negative. So 1 times 5 is 5. If I had a positive 1 and a negative 5, that would make that negative 4. So we set up our 2 parentheses and we split our x's apart, x and plug in +1 minus 5. So remember, if you were to FOIL and go back through that, you would get that same polynomial that you had when you pulled out the negative. Okay, so then we can set those factors equal to 0 and solve. And so my whole point really of going ahead and applying this to this homework is just to introduce to you some new terminology that really means the same thing. So when we were solving a quadratic equation, we were solving for x, right? Where there's so many things that actually applies to, and we just call finding the real zeros, which just means you zeroed out that polynomial when you solved for x, right? And we did talk about that. I said when we solve for x, that would zero out that polynomial, right? So we can call them zeros, and we can also call them x-intercepts. So with parabolas, that's kind of fun, because if you have a coordinate plane, they're crossing the x-axis at a couple spots, right? And so understanding how all of that relates to a parabola is kind of helpful, right? So if we plugged in 0 for our function, which we're used to calling y, I plug that in there, you make 2 ordered pairs out of it. It could be -1, 0, and 5, 0. So there's a question that kind of goes over that. It's mostly to introduce it to you, because we're going to talk about it a lot more a little bit later in this class. Not quite with parabolas, but with higher degree polynomials, but it still applies to parabolas. So what's great is whenever we start working with higher degree polynomials, is the whole point of solving for x, and we have to do it sometimes in a different way because maybe it's not a polynomial we can factor, but the whole point of solving for x is to figure out these points on the x-axis, which I haven't been really good at showing that with parabolas, and I want to get better at it, so I'm going to alter my notes a little bit and wanted to just introduce it to you with this extra note today. So we're going to move on to 2.5. Don't forget that 2.4 is due tonight. 2.5 is mostly just talking about a graph being symmetric with respect to either the y-axis, the x-axis, or the origin, which it's not in bold, but maybe it should be. So if a graph is symmetric in respect to the y-axis, you'll be given, let's call this the given ordered pair. What happens is, if it's in respect to the y-axis, that would be like this example right here. If you folded this graph in half on the y-axis, then that means these 2 points would lay on top of each other, right? So what happens is your x part of the ordered pair would be the opposite sign. Doesn't mean it'll necessarily be negative, because maybe you were given this point, okay, and it might be positive, the x point, because they're on the opposite side of the y-axis. So you'd move to the right instead of the left. If a graph is symmetric with respect to the x-axis, that would be like right here. Again, if we were folding this graph in half, but you'd be doing it horizontally, these 2 points would be matched up. So whatever your given point is, which we always just show with positives, then that means your y part would be the opposite sign. So the x and y values are the same numbers. It's just the signs of the numbers that we're really focusing on. If it's in respect to the origin, which is a really hard thing for me to draw because it's a two-dimensional, if I could turn and turn again and twist it, that would be in respect to the origin. And what you're going to find is whatever point you're given, you're going to change both the x and the y part. And really everything we go off of today just derives from those three concepts. It's really one concept, but three because it's either in respect to the y, the x, or the origin. Knowing that what sign changes with the coordinate pair that you're given. So right here, if you look at the bottom part of your notes, there's three graphs. It says determine whether the graph is symmetric with respect to the x-axis, the y-axis, or the origin. And so you can kind of see some similarities to some graphs that you can compare, but like the origin always kind of looks like a wave because they're in diagonal quadrants, right? So like if you just pick a point here and here, I really like to go off of what I was saying with the sign rules of your coordinates. So like, let's say that this is one, let's say they go up 1 unit each. I don't think the graphs really did originally, but I don't want to go up by halves. So if this ordered pair point was really 3, 2, then this one should have, if it's in respect to the origin, the same numbers with opposite signs. Okay, so that's what we learned right here. Same signs, and I did start with the positives this time. So this should be -3, so 1, 2, 3, which it is, -2, which it is. So that's just kind of looking at it, and you would have to identify those points that I put a dot on. Like you have to find those points yourself and compare their ordered pairs and their signs. So this one would be the origin. Obviously you could probably tell the middle graph is in respect to the y-axis. These are a lot easier to see, I think, because you can kind of see where you could fold that graph. But double check it with an ordered pair and practice those sign rules with those coordinates. So like, let's say I was looking at this point, it's a -2, 0. If it's in respect to the y-axis, the y stays the same, but you can't change the 0 anyways, but your x changes its sign, so it would be a +2, 0. So there's that rule that I was teaching up here in that first bullet or whatever it is. Kind of looks like an arrow. And then again, try to pick 2 points that look like, kind of see how you could fold this on the x-axis. You could fold it horizontally, and these 2 points would probably meet up. But I like to confirm it with an ordered pair. So I'm going to make this 1, 2, 3, 4. So this is over 4 and maybe up 1. But over here, this would still be over 4, but down 1. So if this is in respect to the x-axis, my x's stay the same and my y part changes signs. And I forgot to write y-axis for this one. So there's just so much we're going to do with that concept from here on out for this 2.5. And different ways you can apply that and practice it. Not real hard, but just different ways you can. So like, let's say you were told to consider this point, and really in WebAssign, this will already be plotted for you. So like you would have to go identify that the given point is 7, -4, 1, 2, 3, 4, 5, 6, 7, down 4. So still very similar, but this would be given to you. And you would have to identify, okay, my given point is at 7, -4, which you're capable of doing. It doesn't have to be given to you in ordered pair to be able to. But then part A says, let's plot the image of that point in respect to the y-axis. So find a memory device or whatever helps you. But if it's in respect to the y-axis, that means the y stays the same. So this is what's given. I'm going to do it for all of these. The y will stay the same, but your x changes. So it's -7, -4. So we would need to go to the left, 7. Oh, my old eyes. 1, 2, 3, 4, 5, 6, 7, down 4. So if this isn't just right, let's pretend it is. I need to make those lines darker, don't I? That would also be a goal. It's a goal of mine. So you're just gonna have to use the dot tool in WebAssign to plot that point in respect to your y-axis. Okay, now we use the same exact ordered pair because it doesn't, we're just practicing all of them with different instructions. So this is 7, down -4. Again, this would be given to you, and you would say, oh, this was 7, -4. That was my given point, but they want me to plot it this time in respect to the x-axis. So this is where your x stays the same and your y changes. So instead of a -4, we get a +4. So we'd go over 7, but up 4. 1, 2, 3, 4. So this would be like the point you're trying to plot in WebAssign, kind of like this one would have been. And then finally, 1, 2, 3, 4, 5, 6, 7, down 4. The last example was to do the origin. So again, this would be the given point. You would identify that's 0.7, -4, and then you would say, well, if I want to plot this image in respect to the origin, I would change the signs of both. So a -7 and a +4. So we need to go to the left 7. 1, 2, 3, 4, 5, 6, 7, up 4. So that would be the point that would represent in respect to the origin. And again, I just usually highlight both axis to kind of show that. If you could turn and twist it, it'll be in a diagonal quadrant when it's in respect to the origin. So I have added another note, and it comes from an example that's in your homework, because I've only been doing this in the past, and then whenever you're asked to graph a parabola in respect to like the x or the y origin, it's like we forget that we know how to identify points on a graph, and then use those rules with the signs that we do. So I like to practice that with you. So this looks a little bit different. Earlier I did sketch one. If you would like to sketch this down, you may just make yourself a quick coordinate plane, and let's identify the vertex together, and then you could plot that point. So you need to maybe sketch this given sketch by a couple points I'm going to give you. So if we go to the left, 1, 2, down 5, your vertex is at -2, 5. So you have to kind of look at the graph yourself in WebAssign and find some ordered pairs that are definite points on that parabola. And sometimes that can be tricky because, like, if you look here, especially if you have old eyes like mine, you might think that you're getting close to the origin here, but notice there is a gap. To me, it looks like there's a pretty definite point right here. Okay, so let's go identify what that point would be, which would be like 0, -1. And then, whatever's symmetric to it, just to the left, that point should also be an exact point, not like a partial half or something. So I would go to the left, -4, down 1, so its point would be -4, -1. And so I'm showing you this because while it was more than 1 point and it's actually a parabola, it's really similar to the dot we just did. Okay, you need to go look at the graph and identify 2 or 3 points, at least 2, the vertex being 1 for sure, and then at least 1 other point, but I would still I would do 3 because these are symmetric to each other, right? Remember when you guys learned about that line of symmetry right here, right? That's why I would do that, because it just kind of shows the 2 points that would be across from each other. Okay, so if they told us to graph this in respect to the x-axis, that means this parabola is going to flip over. So what does that mean? So if the vertex was -2, -5, and if it's in respect to the x-axis, then that means our x stays the same, and we're going to change the y part. So -2, 5. So you can go over 2, but you're going to go up 5. 1, 2, 3, 4, 5, right here. Okay, if you did any of these other 2 pairs, so like say 0, -1, your x stays the same and your y changes. So 0, 1 would be another point that you could plot. So 0, 1 would be here. Maybe I should have done this in red. I will draw the parabola in red, I guess. And if this given point was -4, -1, again, if it's in respect to the x-axis, the x part stays the same, the y changes. So -4, 1. So it should be right across from this one. So -4, 1. And that doesn't really look like it's right on that. Oh, it won't be. I don't know. I blanked out in my mind for a minute there. Okay, so you'll see how it's opening down, and it looks like this. So in WebAssign, I don't have the toolbar or WebAssign pulled up right now, and I don't want to do that and waste your time, but you'll use the parabola tool to graph it, and you'll only have to click two points, because it'll make it symmetric because it knows it's a parabola, right? So you definitely start with clicking your vertex first, and then when you click the second point, it'll make the blue parabola. So whenever you choose this parabola tool in WebAssign, when you make the first click, you don't know that it's going to make the parabola graph. You have to make the second click, and then you'll see the blue lines graphed for you, okay? You guys are smart, use technology, I know you can figure it out. So that's how you will, sketch a parabola in respect to like an x-axis or a y-axis. I mean, or it could be the origin, but generally for now, we just kind of focus on the x-axis. So not too hard, but I like to show it because when we just do 1 point, we don't think about how that can apply to, there's all sorts of points on a parabola, right? You can do it to all the points if you want it. Okay, so we can also do tests for symmetry with respect to the origin in an algebraic way, and it still goes along with understanding like the change of that x or y sign. So actually it looks like I need to come back to this page. Not on the origin yet. Let's go to x and y's. Forgot that I turned it to a whole different page and left out this bottom. So tests for symmetry in respect to a coordinate axis. So the y-axis, it's in respect to the y. If when you replace the x with a negative, it leaves it unaltered. So what this means is let's just go show you. If I'm testing, is this equation going to be symmetric in respect to the y-axis? What I do is I keep the y the same, and I change my x variable to a negative, and then I simplify it, meaning if I were to take a negative times a negative, that means this would still really be a positive x squared plus 12. So, and what it meant was if it leaves the equation unaltered, which it did, then we could say it was in respect to the y-axis. I always like to show the other one to show what would happen if it wasn't, like a failed one that altered it. So for this one, that would be if we tested to see if it was in respect to the x, because if it's in respect to the y, it's not in respect to the x, okay? Lots of x's and y's being said today. So we're gonna replace the y with a negative and go simplify and test to see if it leaves the equation unaltered or not. So if we were to go simplify this and say, well, I really need my y to be a positive, that means I would divide everything by a negative. And what you're gonna notice is that with this one, it changes both the sign values. It altered the equation. So it is not in respect. So I'm just gonna put not because I ran out of room. We already proved that it was in respect to that y-axis first, right? So that's how we will test algebraically if the graph of an equation is symmetric in respect to the y or the x-axis. So we're just changing the value, the sign value of the x or the y, depending on which one you're testing, and seeing if it alters the equation. So let's do it with letter B. So if I'm checking to see if it's in symmetric to the y-axis, I like to write that so you can see clearly that that means I'm keeping the y the same. And I'm changing my x. So this would be like saying negative x equals the absolute value of y minus 2. So similar to when we did this, I don't want my x to be negative. I want it to be positive, trying to get it back to the same form, see if I can by using our rules of solving equations. So this would actually make this whole term out in front a negative, so I'd be like saying the opposite of the absolute value of y. A negative divided by negative makes that a positive 2. So it changed everything, really, right? Even if you went and simplified the absolute value part, the constant is different. Okay, so this one alters the equation, so it cannot be symmetric in respect to the y-axis. So let's go see if it is in respect to the x-axis, and that's where the x stays the same, but the y changes, and the y is inside that absolute value bracket. So I just kind of want to remind you, like, if I were to simplify this, the absolute value of y is y, right? And same as this, the absolute value of y is y. So by putting a negative inside the absolute value bracket for this one, just remembering what that means even, a little bit of a review. If you simplified them in that next step, they both still look exactly the same, right? So it doesn't alter the equation, or it does not alter the equation, it's unaltered. So we would say it's in respect to the x-axis. So much fun, right? It's just changing your x and y signs. And if you have a memory device, whatever it is that you're applying it to, you can always do it. Like I think that that's basically the foundation of like the symmetry rule that we're learning today, if you haven't learned it prior. Okay, so origin, remember? First page, we learned if x's and y's are changed, right? So in this one, if we are testing to see if it's in respect to the origin, we're going to change both x and y to negatives and then simplify to see if it's unaltered or not. So like this would be a negative x times a negative y equals 4, and we know a negative times a negative makes that a positive. So a lot of this is just working with your lovely sign rules, right? Simplifying, working with, remembering our sign rules. So this is unaltered. This looks exactly like it started with, so it is in respect to the origin. This one is symmetric in respect to the origin. So we'll do another one. We always like to show you failed ones, I guess. So I bet you could tell that this one would be a failed one, but we'll go through the motions. So we have negative y equals a negative x to the third power plus 1. So again, I just changed the x and y's, both of them, because we're testing to see if it's in respect to the origin. So that tells me that's the key indicator of what signs we're changing. And so if we go simplify this one, you'll notice first we need to simplify negative x to the third. Well, that's still going to be a negative. A negative times a negative times a negative is still a negative x. So we can get rid of that parentheses. And then we would want to divide by a negative 1 to try to get y positive. So we'd get y equals a positive x to the third, but then we get a negative 1. So because we got these two things that are different, then that means it did alter the equation. So it's not in respect to the origin. Or you could just write no for yourself if you want. You don't want to write all that. Okay, so just a couple other things that really go along with this, and I will be honest with you, I always am. We don't do a whole lot with odd and even functions, but it's still just using those same rules. I actually skipped over it in my hour before you guys, but I'm going to go ahead and cover it with you all. So it says even and odd functions. Some functions are classified as even or odd. So basically what this means is an even function is when you change the x value and your y stays the same. Okay, like if you plug a negative in and it came out and was a positive y, that's what this would mean. An odd function is if you change the x, it will change the y, which would be like in respect to the origin, which is what I should have written up here. So remember, if you change the x value and the y stays the same, that means it would be in respect to the y-axis. So I'm just trying to show you that these even and odd functions are basically the same concept, just talking about a different theory or rule that is sometimes used. So sometimes they classify them as even or odd. So like letter A, if I were to change this to a negative x and cube it, I would get out a negative solution, right? So it's like those input and outputs. If you plug in a negative, that's going to be like a negative x. If it gives you a negative output, that would be like a negative y. Okay, so this one would be an odd function, because when you plugged in a negative, your solution became negative. So odd functions are in respect to the origin. That's just a rule I like to tie it to because we just been going over that quite a bit. So also it looks like this graph here. The graph of an odd function is symmetric in respect to the origin. So if you had 2 points, you were comparing something like that. Part B is if you plug in a negative for this one, we have a negative inside that absolute value bracket. Remember, that could still just be x. Even if you simplified this, the absolute value of x, right? If we didn't change it, just showing you, is also x, right? So if you change x, it still doesn't change the output. So when you change the input, but the output doesn't change, I'm going to do that because it's negative. Maybe you could do positive. Think of change and not change with positives and negatives. Then that means it was in respect to the y-axis, which means it's an even function. I do memory devices, so sometimes I just That's what makes me think of it as an even function, is that was in respect to the y-axis. So like this one would be in respect to the y-axis, these two. This is an even function, I'll make it bigger, and this was an odd function. There also can be neithers, meaning it just shifted. And that would be like if, a lot of times there's more than one term when that happens, not just one single term. So if you were to go change x for both of these, when you simplify it, this term is not changed, but this one is when you simplify. So even if you pulled out a negative, it's like the whole thing is changed in a sense, but not really, because it would change those signs again. So both of those signs are changed. So this one would just be a neither. So we could have neither. And this would be basically one that would be just shifted probably to the left. So those are even and odd functions. I don't know, I'm always tempted to just take it out of our notes because we don't really do much more with that concept, but since other math instructors teach it still, I am. Just another layer of something you already know, right? Calling it something different, kind of like with when we solved for solutions for quadratics, we just called it a solution when we were way back in 1.3 with the quadratic section, but I introduced to you today that they could also be called zeros. That's the fun of math, right? Language. So we're also talking a little bit about translations. We do more of this later. We don't do much of it now. I always wonder why it's in this, because we're really talking more about reflections and symmetry than we do here. So I'm going to quickly go over it, but just know you don't have any translations in your homework. Okay. So parent functions, you guys heard of parent functions before? It's like kind of like the parent of the graph. So this parent function is like the function of x equals 2 to the x power. It's really small, so maybe you want to rewrite it. And that graph looks like that gray line. So if you were to subtract from the entire term that has the x, then that means this would shift up or down. So this one has a -3, so it shifted down 3 places. So you can see how you have a point here. If I go down 3, 1, 2, 3, it would translate down, and it kind of looks a little bit different, but just shifted down. If we subtract from the actual variable, so again, this is the function of x equals 2x was the parent function. And what they've done to this graph, and I'm going to rewrite it, they say g of x to show it's a different function equals 2 to the x power, but you're subtracting from x. It's not because you're up in the exponent, and you're going to see that over here. It's the difference of, this one was saying capital F of x function 2x, it was subtracting from the entire term, not the x itself. So that's the difference between the two, even though they look really, really similar, don't they? This represents right or left movement, horizontal movement, and the opposite of what you would think. So like a -3 really means you're moving right 3 places. So if you have a point here and you go over 3 places, you can see where you would land on that graph. So like I said, we'll do translations a little bit more, but I guess we're just introducing it since we're talking a little bit about characteristics of graphs in this 2.5 stuff, but mostly with symmetry. So I'm only going to compare the vertex of this parent graph, and it says to use the graph of G, that's what this graph is, to sketch these graphs, okay? So this one is saying G of x -2, so it's not being subtracted from the x like this one is. When it's from the x, it'd be like in a parentheses with it, okay? Probably like that. So this would represent a down 2 places, 1, 2, and to be really accurate, you could probably go find 2 other points, but I'm not going to. This is just to get a sketch, an idea of what's happening. This one is going to move to the right 3 places. So if you have a dot here, we're gonna go to the right 3 places. That would be our vertex for this one, and it would look something like that. So we're just sketching it. Doesn't have to be exact for our notes now. But those are not like symmetry or reflections, right? That means you're taking this graph, if you could just slide it over or down, that's different. Reflections closely resemble symmetry, and really all that we do is pretty much symmetry. We don't do a lot of stuff that's not. So what this is going to show you in this little text box that came from our book, it says the graph of y equals a negative f of x is the graph of reflecting the x-axis. So what this means is, put it in the words that we're used to today. You could probably tell this was in respect to the x-axis. So what this means is your x's are the same and your y becomes the opposite sign. And that's what this means, like you changed the y to a negative. They put the negative in front of the f of x, which is like your solution, okay? This one over here would be symmetric to your y-axis. Do you guys see how I'm saying the same thing over and over again? My son would be like, stop. Which it makes it seem more complicated, I think, than what it is. But it is what it is. So this is in respect to your x-axis. And if we made 2 points, I'm really big on just making your own points. This would be like saying 2, 1. This would be like saying 2, -1. Sorry, x stayed the same, our y changed. Here you can see visually that it's in respect to the y-axis. And again, if we made ordered pairs, you can show that with ordered pairs 2, 0 and -2, 0. So your y stays the same and your x changes. So that's like a reflection. So you do have a question that looks a little bit like this last one. So I'm going to go over it. We'll be done. We still have 5 whole minutes. So here it says reflections, the graph of, remember that's like saying your x stays the same and your y, your solution becomes a negative, is in respect to your x-axis. It's just a repeat of what we set up here. Okay, so that's basically what we've done here. This is like your x. It's like when you plugged in a positive x, your solution became a negative y. So the x is the same, the y changed. So that means, that means this is in respect to the x-axis. So if we were to graph this, this is your x-axis here. And I'm just going to use that starting point right here and just say it would look something like this. You don't actually have to graph it, you just pick the appropriate graph in multiple choice and WebAssign. So what this is stating, this would be like you're plugging a negative in. It's kind of going backwards because the inside of this is a negative x. So this is like saying you have a negative x, but this would be like your y value because it's inside. That's why we know that it goes with the x. And this was outside. That's why it goes with the y. So if our x changed and our y stayed the same, then that means this is in reflex. This is symmetric to the y-axis. So this one right here, so we would plot it over here. So I usually label it with the letters. This would be your x of x or your C graph, and this was your G of x graph. So I will say, like, in my opinion, I wish we spent more time on function notation because of this stuff today. And I do try to go over it, but even when someone takes math functions, which is based on function notation, I don't think there's ever enough practice to really understand what that means. And so I just always try really hard to say, like, when we say function of x, that's your variable, which the whole statement itself, function of x, is meeting a y, which is your solution. And that helps a lot when you're going through trying to figure out, what's really changing, the x or the y. But if all else fails, you don't even have to worry about this fun function notation that they give us in notes. You can just think about the rule we started with today. When I said on that very first page, which I'm trying to get back to it. On the very first page, this rule right here takes you through everything we really did today. Algebraically, yeah, it looked a little bit different, but we still were looking to see if our x term changed. If we changed the sign of the x term, did it change the equation? If I changed the sign of the y and then simplified, did it change the equation?